Achieving de-identification compliance requires isolating protected health information, or PHI, with near-perfect precision. A single missed identifier constitutes a major regulatory violation. Our initial step involves defining the target scope, the 18 HIPAA identifiers. This includes explicit identifiers like names and social security numbers, but also quasi-identifiers such as dates of service and unique device identifiers. The system analyst must map these 18 categories directly to the named entity recognition labels used in the pipeline. We are not aiming for simple masking. We require semantic understanding to differentiate, for example, a patient's age from a dosage amount. This precision dictates the choice between rule-based systems and machine learning models, favoring the latter for clinical narrative complexity. We must establish a zero-tolerance threshold for false negatives, prioritizing recall over precision initially and managing the resulting false positives later in the workflow. Relying solely on regular expressions or regex for PHI redaction is insufficient and introduces unacceptable risk. While regex effectively captures structured identifiers like specific date formats or standardized medical record numbers, it fails catastrophically in contextual environments. For instance, a pattern matching a name structure cannot distinguish between Dr. Smith, the attending physician, and John Smith, the patient. Furthermore, variations in clinical shorthand, misspellings, and non-standard formatting break rigid regex rules instantly. Implementing a comprehensive regex library for all 18 identifiers becomes an unmaintainable engineering burden. We transition immediately to statistical named entity recognition models, which learn context and relationships, providing the necessary robustness for unstructured clinical free text notes. This shift requires specialized model training on annotated clinical corpora, such as the I2B2 datasets, to achieve domain-specific accuracy. Effective redaction demands domain-specific named entity recognition models, moving beyond general language models. We utilize architectures like Clinical BERT or SciSpaCy, which are pre-trained on vast amounts of biomedical literature and electronic health record data. These models excel at identifying entities like patient name, hospital location, and date of service within complex narrative structures. The system analyst must ensure the chosen model's output labels align perfectly with the required 18 HIPAA categories. Model selection is critical. A model trained only on general news text will misclassify clinical terms, leading to high false positive rates or worse, missed PHI. Fine-tuning the base model using a small, highly accurate set of internal institution-specific notes significantly boosts performance, especially for unique local identifiers or specific physician naming conventions. Contextual ambiguity is the primary source of false positives in clinical redaction. Consider the phrase, "The patient's age was 65 and the dosage was 65 milligrams." A naive model might redact the dosage as an age identifier. To mitigate this, implement post-processing rules based on entity relationships. If the model identifies a number followed immediately by a unit of measure, such as mg or units, downgrade its classification as a PHI identifier unless it is explicitly a patient's weight or height. Another critical ambiguity involves differentiating patient names from physician names. Train the model to recognize titles like doctor, MD, or RN as strong indicators of non-patient entities, preventing unnecessary redaction of staff names required for audit trails or operational context. This requires careful feature engineering during the model training phase. The redaction pipeline executes in 3 stages: tokenization, entity span identification, and replacement. Standard tokenizers often break up complex clinical terms, impacting entity recognition accuracy. Use a specialized tokenizer, like one trained on MIMIC-3 data, to maintain clinical context. Once the named entity recognition model returns the character offsets for a protected health information entity, the system replaces the identified span. Crucially, replacement must maintain the original text length to prevent downstream system failures that rely on fixed character offsets or indexing. Replace the identified span with a consistent length-preserving placeholder, such as a sequence of X characters or a standardized tag like patient name. This ensures database integrity and prevents index misalignment during subsequent data processing steps.
Maintaining character offset integrity is non-negotiable for systems that rely on text indexing, search functionality, or annotation layers. When replacing a span of text, the replacement string must occupy the exact same number of characters as the original protected health information entity. If Jane Doe, 8 characters, is replaced by name, 6 characters, all subsequent character offsets in the document shift by 2 positions, corrupting indices. Implement a padding mechanism. If the replacement tag is shorter than the original entity, pad the tag with spaces or a neutral character to match the original length. For example, Jane Doe becomes name space space. This guarantees that the redacted text can be stored and indexed without requiring a full reindexing of the entire database, saving significant computational overhead and ensuring search relevance remains accurate. Not all named entity recognition predictions are equally reliable. Implement a confidence scoring threshold to manage risk. Entities identified with a confidence score above 0.95 are automatically redacted and committed to the database. Entities scoring between 0.80 and 0.95 are flagged as high risk and routed to a human review queue for manual validation and correction. Scores below 0.80 are typically discarded as low confidence noise, unless the entity type is extremely sensitive, such as social security numbers, where the threshold must be lowered to prioritize recall. The human review interface must display the original text, the identified span, the entity type, and the confidence score, allowing reviewers to quickly accept, reject, or modify the redaction boundary. This hybrid approach balances automation efficiency with regulatory compliance. The redaction service must operate as a high-throughput, low-latency microservice, especially when processing real-time clinical documentation. Avoid synchronous processing where possible. Integrate the service using asynchronous messaging queues, such as Kafka, where clinical notes are pushed for redaction and the resulting de-identified text is returned to a separate topic. Model inference speed is critical. Deploy the named entity recognition model using optimized frameworks like ONNX or TensorFlow Lite, leveraging graphics processing unit acceleration for batch processing. Target an end-to-end latency of under 50 milliseconds per note to prevent bottlenecks in the electronic health record system's data ingestion pipeline. Monitor queue depth and processing time metrics continuously to scale the service horizontally during peak usage hours. Regulatory requirements mandate the ability to reverse the de-identification process for auditing or specific legal requests. Do not simply overwrite the original text. Store the original unredacted note in a secure, access-controlled vault, separate from the de-identified data store. The audit trail must log the unique identifier of the note, the specific character offsets of every redacted span, the entity type assigned, and the confidence score of the prediction. This mapping allows for precise programmatic reversal of the redaction if necessary, without exposing the original data to the general application layer. Implement strict encryption and access controls, such as role-based access control, on the vault containing the original notes, ensuring only authorized compliance officers can initiate the reversal process. Sustained high performance requires continuous optimization of the inference engine. Profile the named entity recognition model to identify bottlenecks, often related to input-output operations or memory allocation during batch processing. Utilize quantization techniques to reduce the model size and memory footprint without significant loss of accuracy, enabling faster loading and execution times. If deploying on cloud infrastructure, select machine types optimized for machine learning inference, specifically those offering dedicated graphics processing unit resources. Implement a caching layer for frequently processed static documents or templates to avoid redundant processing. Finally, establish a retraining schedule, ideally quarterly, to incorporate new clinical terminology and maintain model accuracy against evolving documentation styles, preventing model drift and subsequent compliance failures.